Okay, so today we're actually going to finish up not only chapter five, but all of the new material for the entire course. So it's hard to believe where did the time go? But yes, we're just about done. So what remains is sections five, seven, and eight, and then that will be all the new material. So now, of course, the course doesn't end for about 2 more weeks. So let's go back and look at um, Cengage and see what's still due. Hold on one second. God, I've got so much stuff open. I'll have to find it. Hold on. There it is. Okay. So, if we look at this list now, today is the 12th. So tonight you're expected to do for one, three, and five. Okay, great. So, like I said, right now we're going to finish five, seven, and five, eight. So there's nothing else new to do. But if you look ahead, you'll see that next weekend you'll be expected to do five dash one, two, three, and four. Ooh, plus the midterm. That sounds like a lot, but they're open now, so you can go ahead and get started early. And then the following weekend, you'll have the rest of chapter five, five, six, seven, eight, and nine. Sorry, five. Remember, there's no five, nine. Five, five, six, seven, and eight, and the final exam. That's the 26th. I think the class officially ends on Monday, the 27th. So the grades have to be in like right after that. So that's the last realistic due date that I can give you. But still, you got 2 weeks. And so it'll be a little intense, but you can do it. So far, it looks like people are doing very well. That's good to know. So what is left to cover? We've got this notion of inverse trig functions to look at. So what exactly is an inverse trig function? All right, well, you've probably run into these before. For example, let's just say, let me make a quick example. All right, oh, wait, hold on. I'm in the wrong mode here with my calculator. Okay, so for example, if I told you that the sine of 90 degrees is 1, then the function arc sine, which is sometimes written like this in some books, and on your calculator, it's written like this. And that this notation reinforces the idea that the sine and the arc sine are inverses of each other. Okay. Oh, actually, sorry. If the sine of 90 is 1, then what I would be trying to calculate is the arc sine of 1, and that would bring me back to 90. Okay, so that's how it works. If the sine of 90 is 1, then the arc sine of 1 is 90. And of course, there's one for all the trig functions. They have an arc, an inverse. For example, if the cosine of, let's say, the cosine of 90 it turns out to be 0, then you could turn around and say that the arc cosine, which, whoops, of 0, not 90, 0, would be 90 degrees. Okay, so these arc functions are inverses of the basic trig functions. Okay, and there's one for each. There's an arc sine, an arc cosine, an arc tangent, an arc cotangent, arc secant, and arc cosecant. And in each case, this is how they're defined. Now, you've run into these before, most likely, but what we're going to do differently now is we're going to see how to calculate the derivatives of these inverse trig functions and their integrals. Okay. And as it turns out, you might think this is a very obscure topic, but the reality is this is going to be very, very helpful in Calc 2. When you start tackling much more advanced integrals, you'll see that these arc trig functions are very, very helpful. Okay, so we don't want to neglect this topic. Anyway, so let's begin at the beginning. We'll start with differentiation. Now, by the way, here's one thing we have to be extremely careful about. A quick reminder that when you have functions that are inverses of each other, um, let's say that we have g of f, f of x and g of x. If the following two statements are true, this implies that f of x and g of x are inverses. It also implies this important result. The domain of f of x is the range of g of x, and the range of g of x, f of x. I know we went over this a while back, but it's been a while. So the range of f of x equals the domain of g of x. Why does that matter so much? Because with the arc or the inverse trig functions, there's usually very tight restrictions on their ranges and domains. They may not be defined over certain intervals, so we have to be extremely careful here. In fact, I think they have some graphs here so we can see this more easily. Yes, they do. So here we go. So you can see that the arc sine has a domain only between negative and positive 1. The arc cosine, same thing. The arctan is defined, it has a domain over the entire real number line, but the ranges are also very tightly restricted here between positive and negative pi over 2, 0 and pi, and negative pi over 2 and pi over 2. Down here, you can see that there's actually discontinuities in the first two. So, and like I said, you just have to be very careful when you solve for these derivatives and integrals that you don't find yourself outside of the domain or range of the function. All right, so with all that being said, this is the formal definition of these functions. And so this is a little bit more formal. And if you notice this IFF here, let's just use this as our starting point. Let's see. God, where is it? Oh, here it is. So what exactly does that mean? Okay, so here's how this works. I'll put this in quotes because it's clearly not a real English word. And it's shorthand for the following. So in other words, this arrow is pronounced implies that. So y equals arc sine of x implies that sine y equals x, but it also goes both ways in this case. In other words, y equals arc sine x implies that sine y equals x, and sine y equals x implies that y equals arc sine x. Now, sometimes you see this written in the following way with a two-headed arrow, and that means that the causality goes both ways, okay? Or the implication goes both ways. And so this is often written in English as IFF for if and only if. Okay, so when you see IFF with two F's, that means the implication goes both ways. Okay, so that's what this is trying to tell us. And then they're also helping us by showing us the range in the domain so we don't get into trouble. Okay, and then you can see they're all equally defined. All right. So again, I think having these pictures here is going to be very helpful so we know what to avoid, in other words, where all these functions are defined and to watch out for these discontinuities. So here we go. Now, what I'm going to do here is show you how to do this on your calculator first. All right, so let's try that. So on the TI-84, um, if you notice, there's three buttons, sine, three trig functions. Directly above them, in tiny little print, this is how you know what the second function is. If you look over there, this calculator has a second button in the upper left-hand corner. And the way you access these functions is to hit the second and then that button. So here's what you would have to do. Second, sine. All right. And then what would be the result? Negative 30, which is degrees. All right. If you've got it in radians mode, you're going to get the equivalent number of radians, whatever that is. I think it'll be easier here to stick with degrees. So just remember, if you go back to the top under mode, there's a lot of modes in there. If you go down to the number four, row number four, you get to choose between radian and degree. So you should always make sure you know which one you're in before you do anything. Just make sure that otherwise your results will look very strange. Um, like if I switch this to radians right now and run it again, it comes up negative 0.523. It's a mess. All right. But this is radians. Just keep that in mind. These are degrees, these are radians. Actually, it's a fraction of pi. Okay. So anyway, um, oh, what do you know? It says here that it's pi over 6. Is that right? Let's try it. Well, what do you know? That's exactly, I didn't recognize it. Negative pi over 6. All right. So if they want the answer in radians, it's negative pi over 6. If they want degrees, it's negative 30. Okay. So it's just a question of making sure you're in the right mode. Either that, or if you remember how this works, So in other words, that implies that pi over 6 radians is 30 degrees. So we could have figured it out that way. In fact, that's how it was done before calculators came along. All right. Arc cosine 0. So hit second cosine 0. All right, let's see what that gives us. Right now I'm in the radians mode. Uh, 1.5707. I'm sure that's a function of radical 2. Let me just double check. Actually, I'll tell you, first let me put it in degrees mode just to see what it says there. Okay, so it's 90 degrees. Okay, I get it. So in other words, that's actually half of pi. And again, you can see why that would have to be the case because pi radians is 180. So therefore, pi over 2 is 90 degrees. All right, so I think that's enough of that. Let's get on to something else. But they are, of course, reminding you that we have to make sure we stay within the domain. All right, one more. Arctan radical 3. Um, second tangent. Now for this, there is a radical button on here. If you hit second x squared, it'll show a little radical sign. And then you hit 3. Right, second tan, second x squared 3. Oops. 60 degrees. The only thing you got to watch out for is after you enter this, you may have to use arrow key, the right arrow key, to get outside of the radical. Otherwise, it might not give you an answer. So just push it over there until it's out of the radical. So it's 60 degrees, which is, as you can see, is pi over 3 radians from this relationship. Okay, I think that's all the examples that we need. Um, all right, I think that's enough. Okay. And so here, oh, this is interesting. They're saying here's how you can work. If you want to use your cleverness to solve for some of these, look what they're doing here. Knowing that the arctan and the tangent are inverses of each other, if I take the tangent of both sides, the tan and the arctan effectively cancel each other out. So I'm left with 2x minus 3. The tangent of pi over 4 is 1, and we can easily solve for 2. So there's a way that this can be very helpful to us when we have these incredibly messy functions involving tangents, arctan, whatever. Now, finally, we get to do some derivatives. So keep in mind, u here is a function of x, so we do need, um, well, u prime, which is du dx. Let's copy these. So just as we've done seen before with U substitution problems, U is a function of X. U prime means the same thing as du dx. Okay. So I guess they have some examples for us. Yes, they do. So let's start with arc sine 2x. So here U is the 2x, du dx is 2. Okay. All right. So after we make all the substitutions, we can rewrite this as, and that's it. We're done. All right. Well, that wasn't too bad. All right. Let's try this one. So in this case, the U is the 3x. And so the formula we need is the second one, U prime over 1 plus U squared. Not bad. It wasn't that difficult because it's the part of the reason why it's so easy is because it's clear which rule we're supposed to use. When you start doing integration with these, well, then it starts to become more of a challenge because it's not always obvious which one you're looking at. Okay, so, but here we know exactly what we're trying to do. All right, so the arcsine formula is this one, U prime over radical 1 minus U squared. Okay, let me just double check. Arcsine, yeah, U prime over 1 minus U squared. So U, all right, so we're going to have, all right, so they've decided to go ahead and simplify it a little bit, and that's fine. And oh, so they multiply them together. I mean, this is where we are. I guess you could do this too if you want, but either one of these is fine. All right, and then there's one more, the arc. Ooh, the arc secant. We haven't seen that one yet. Now, of course, nobody expects you to memorize these. Let's see, what do we have here? U prime. Okay, so that's the derivative of the arc secant. So here, U is e to the 2x. du dx by the chain rule is 2e to the 2x. Okay, because what do you have here? We've got e to the u, so it becomes e to the u du, and that du is 2. Now, they do point out in the book that e to the 2x is guaranteed to be positive, so we can drop the absolute value signs. All right, here we go. So it becomes, and yeah, there's some cancellation going on here. And that should do it. One thing I do want to point out here, just be careful with this. If you have a to the m power raised to the n power, it becomes a to the m times n. So here you end up with 4x. Okay, just be careful with that. And so this is our final answer. Beautiful. So that wasn't too bad. Oh, there's one more. Okay. Oh no, this is a different one. They're saying here that well, I guess it turned into this catastrophe, and they're just showing you that, of course, with algebra, we can simplify it if we want to. And, you should try whenever you can, but you can see this one's kind of a mess, but they did manage to clean it up and get it down to this. Now, here, they've decided that since this is the end of the course, basically, they would like you to have a quick overview of all the derivatives that you've learned during the course, all in one nice, convenient place. Okay, so this is basically all of the rules that we've done. Looks familiar, don't they? It's a very long list, isn't it? Okay, so if you need this for when you're working on, let's say, your exams or any other problems, it might be nice to print this out and have this right in front of you. So keep in mind, this is 5.7, slides number 23, 4, 5, and 6. They're all right here in one convenient location for you to use. And just remember, too, that u is a function of x. So now here they're challenging us to do this without a calculator. Hmm, not sure I get why they want us to do this, but see, then you'd have to figure out the angle. So what you're being asked to do is find the angle whose cosine is radical 2 over 2. I guess if we had the unit circle in front of us, we could do that, but I think we might as well just use the calculator. So let's see what it is. So remember, it's second cosine. Yeah, I'm not sure what the point of that was. Now, by the way, don't forget it does have a square root button, open parentheses, second x squared 2. All right, that should take care of it. But again, here's what you're going to have to do. After you create this radical 2, um, use the arrow key to move outside of the radical. It's drawing a little picture of a radical, and you'll stay stuck in there until you move it out with the arrow key. That's something, if you didn't know that, you'd be stuck forever to remove out of radical. Then you can go ahead and apply the division, and I got 45 degrees or pi over 4 radians, which is C. Okay, great. Um, the derivative. All right, let's grab this one. All right, so we have to go back to our list. Actually, we could grab it from here too. This is an arc sine. Just so happens to be right here. Now, of course, the constant, the 13, you can keep that on the outside. Don't worry about that until the end. So you're going to have, all right, then we can apply the rules. U prime is 1. All right, so unless they simplified it, that should do it. Yes, they did. They simplified it. Okay. So you could apply FOIL here. F is x squared. O is -1. Sorry, negative x. I is negative x. And last would be 1. Oops. So that would be squared minus 2x plus 1. So when we drop the parentheses, we have 1 minus x squared plus 2x minus 1, or just um, minus x squared plus 2x. So this can become 13 over. All right, and that would be B. Okay, they just rewrote it slightly differently. All right, so that would be B. Oops. And yes, there we are. Okay, so now that leaves us with 5.8, where we look at integration. We reverse the process. But of course, we know that integration is a much messier operation than differentiation. A lot of the challenge comes down to recognizing which form we're working with. So let's see how that works. All right, let's go get that one. Okay, so they're going to give us some of the rules right here. And you can see they're just reversing the ones we just learned. A is a constant, U is a function of X. There's six of them all. Oh, they're only showing us the first three. Hold on. Oh, right, right, right. Yeah. Okay. So they're going to start with these. There's many more, but we're going to start with these three. All right, let's look at this one. So let's go back and look at the list. How do we know which one of these is the right one? That's the biggest challenge. That's always going to be the biggest challenge with integration. Which of these many, many, many formulas should we use? There's so many. If you look in the back of the book, there's a full list of 100 of these for us to choose from. So it's like, well, which one do we use? Well, if you think of this as a, let's say a squared, and then let u be x, then this one takes the form, and that of course means that du equals dx. That would put us here. So is that one of our basic formulas? Why, yes, it is. Look at that right there. So in other words, by writing it like that, it's obvious that this is an arcsine problem. So u is x, a is 2, and we're done. So the whole thing was rewriting it in terms of x and x, a is a constant, and lining it up with one of these formulas. Okay. So this takes a lot of practice to get good at. You're going to need a lot of that in Calc 2, by the way. You'll be constantly rewriting these integrals to hopefully find a formula that you can use from the tables. If one of the other techniques that you learn doesn't work, okay, so the tables are there almost as a last resort if you can't find any other way to approach them. All right. So what else do they have for us? Number two. Yeah, sometimes you'll be saying, what am I supposed to do with this thing? It's really look at the tables and see which one makes sense. So here, I'm going to be a little careful here because now if we're going to try that approach, A would be radical 2, so that when it's squared, it becomes 2. And then U would be 3x. And so we've got to ask ourselves if there's a formula for, oh, oh, yeah, see, there's the thing. That means that du is 3 dx. So we'd have to rewrite it like this. And then we would have, so is that one of our formulas? Why, yes, it is. It's the arctan. Look at that. So that means we have So we chose A to be radical 2. U is 3x. Um, A is radical 2. And now I'm sure they're going to expect us to clean it up a little bit. So here we're going to use this approach called rationalizing the denominator because we don't want radical 2's in the denominator. They're irrational numbers, and by convention, we try to avoid having those in the denominator of any expression. How do we get rid of it? We multiply by a specially chosen form of 1. And then for the other one, same thing. And so we'll replace those with, and there it is. Okay, in the full form, the correct form, the preferred form. Let's put it that way. Oh my God, they left it in the original form. I can't believe it. Oh, you don't see that every day. Often, mathematicians are kind of purists. So, but anyway, so I guess this wasn't completely necessary, but it's common practice to get those denominators to be rational numbers only. So I guess if they'll accept this, that's fine then. I'm not sure if MindTap will or WebAssign will insist on this. Either way, it's fine. And then C, God, what's going on here? All right, so let's try this. Let's try U as X. No, it would have to be 2X. Yeah, so we got this extra X out here. So, so if we do it this way, now these might not be the right substitutions. We may have to try it again, but here we have du. This is actually u over 2. And then this is now u squared minus a squared. And then I've got this 2 here. Dividing by 2 is the same as in the denominator, is the same as multiplying by 2 in the numerator. And now these guys cancel each other out. Well, actually, no, they don't. Yes, they do. Sorry. Yes, they do. So you got, so we got our fingers crossed that one of those formulas is this one. Oh, I think we got a winner right here. Yeah, we did it. All right. So remember, we chose A to be 3. U is 2x. So our final answer is, all right, let's see. 1/3 arcsecant radical absolute value 2x over 3 plus c. Perfect. Whew. So really, in every one of these cases, what we're trying to do is figure out what to do about U and A and make sure that it is in a form that follows one of these formulas. Otherwise, we have to start all over again. Um, now here's a messy one. This one doesn't follow any of the ones we just saw, does it? What can we do? So this is what integration can often be about, trying to find clever ways of rearranging what we have into something that does match up with one of the rules. So what they're suggesting that we do is try U substitution. And okay, so therefore we have, oh, you know what they're doing here? Du over U. Oh, I see where we went wrong. They wanted us to let you, okay. All right, we're gonna have to do this again because they wanted U to be e to the x. Okay, now I get it. See, there's several different ways we could go with this. So they've decided the best bet. And when you see that you're running into trouble like this, you just start with a different U. It happens all the time. If we try instead U equals e to the x, the advantage of doing it that way is that du is simply e to the dx. And this is now u squared. And then dx is du over e to the x, which is du over u. And it just so happens that's the arc secant formula. Let's go back and look at it. Oh, it was in the previous section. Oh, wait, no, it wasn't. It was here. Hold on. There it is. Okay. So, yeah, so remember, A would be one in this case. All right, so we have 1 over 1. Remember, we just finally decided that U would be e to the x. So it's the arc secant. There we go. My God, what a mess that was. Yeah, whew, what a mess that was. Oh my God. Now, sometimes we've got this technique called completing the square. You may have run into this before, which can help us. Um, and what it means is if you have a quadratic expression, you're going to take the middle term, the coefficient of x. Okay, so this is what it becomes. So it looks like they're assuming that A is 1. So let's rewrite it like that. What is this getting us? Well, for certain applications, it's easier to deal with the problem this way. So we'll have algebraically, it doesn't seem like it's getting us anywhere, but it can be very helpful for certain applications. So, like, here's an example. Now, so far, we have not seen this case in any of our rules. So, what they're going to suggest we do is this. This is B. So, the x squared minus 4x plus 7 becomes, oh, wait a minute. Sorry, B is 4. Whoops, let's fix that. Much more like it. Okay. All right. And so what that gets us is plus three. But see, the reason why they're doing this is because then suddenly u can be set equal to x minus 2, and a can be set equal to radical 3. So that u squared is, of course, x minus 2 squared, and a squared is 3. And therefore, this expression here, the original problem, can be rewritten as, oh, and by the way, this implies that du is just dx. And that is the one that we're looking for. Okay, so it looks like that would be the arctan formula. Let's go find it. And there it is. Yes, so we've chosen a to be radical 3. U is x minus 2. And of course, du is, oh, that's right. We don't need it because we're just substituting. And that should do it. Yes. All right. And then they're going to give us a nice little review, just like they did in the previous section, where they gave us a nice list of functions for differentiation. Now they're going to do the same thing with integration. So once again, you've got this nice, helpful table all together in one nice place where you can have all of the stuff in one place. If you want to print this out, you can hold it or keep it in front of you while you're doing your exams or your problem sets. Okay. Oh, all right. So they got another example. All right. So let's say that we decide that u is x, du is dx, a would be 2. That means this reduces to, all right, let's see if this is one of our formulas. Why, there it is right there. All right, so we have, very nice. So again, it's the art form of finding these formulas by possibly rearranging everything algebraically, making the right substitutions for u and a. Okay. 1/2 arcsecant. Yeah, we got it. What about this one? Ah, they tricked us with this one because we don't need any trig functions. If you let u, I think they mean for us to let u be x squared minus 4. And then we'll need to supply 2 here. Oh, I think it's looking good. And of course, we'll apply the power rule. So that leaves us with, and that of course gives us, these drop out. And that's x squared minus 4 under the square root sign. That should do it. Yeah. Okay. So you can see we don't want to get too dependent on these tables. Sometimes we don't need them. This time, straight ahead, U substitution did the trick. Oh, so this was another trick question. They're saying, listen, you don't know how to do this. Okay. Ooh, okay. So I think that would be here. Yeah, that looks really bizarre. It's the log of the log x plus c, but that's the right answer. Oh my God. All right, I think there might be one more here. Yeah, so that means we have u to u. Now, of course, they may want to well, all right, well, let's see what they did. Yeah, okay. And oh, and here's one more that we don't know how to do. All right. All right, so that's that. This is 5.7 and 5.8. So now you're experts in integration and differentiation, at least when it comes to trig functions and inverse trig functions. So now what you have to do is make sure that you finish all these assignments on time. So just be aware. Now we're quite a bit ahead of ourselves. Technically, this shouldn't, I mean, we didn't have to finish this material until 2 weeks from now, but this gives you much more time to get everything finished, I think. So just don't forget that tonight, this weekend, tonight actually, you're doing these three right here. And then next week, we've got five, one, two, three, four, five, one, two, three, four. No, there's four, and a midterm. So keep an eye on that. And then for the last week, 2 weeks from now, you're expected to do the stuff we just did, along with L'Hopital's rule, which we covered last time. And plus the final exam is here. Now, the final exam is only based on the last, if I remember correctly, it's not the whole course. It's based on, I think, just four and five, maybe. I'd have to look it up, but it's like whatever is not on the midterm is on the final, so it's not completely comprehensive. Although it's really hard to not have comprehensive exams in math, it's just focused on those last two chapters. So, it won't be as bad maybe as it sounds, but keep in mind they're all open. You can start them anytime you want, but they're all due ultimately by the end of the course. That would be that Sunday, the 26th. I'm pretty sure that the next day, the 27th, is the official closing date of the course. And then, of course, the grades would be due almost immediately. So, anyway, so as usual, if you want, you can get together with me by Zoom session. You can send me emails if you're not sure. But this is the last new material. So I wish you luck with all the rest of your assignments. And who knows, maybe I'll see you again in the future. Okay, bye.